Today I'm going to talk to you about the customization of deep learning model for code completion task. But let's start with a bit of context, and in particular, let's start by talking about code completion. Because developers spend a lot of time in writing code, understanding the code, and at the same time also finding solution on the internet. This is the reason why a lot of research has been done to speed up the process, in particular the writing process of the developer, and improving their productivities. One of the tasks that is generally supported by tools is the code completion one that works as follows. So let's say that we have an incomplete Java method like this one, and a developer is going to write a new line exactly at this position. A code completion recommender system will recommend the next bit token, the next line, or the next code block that the developer is more likely to write in the given code context. And in this case will be the initialization of the for loop for summing up all the integer in a list. Now, probably one question that will cross your mind just from the first slide is why we are still talking about code completion in 2024. And the reason is pretty simple, because today there exists GitHub Copilot that is considered the state of the art for code completion and code generation that works and also works very well. In particular, just giving a natural language description, GitHub Copilot can generate an entire function which often is very accurate. And it's not just GitHub Copilot, because with the rise of the large language models, there are thousands of tools based on deep learning models that are increasing in size and complexity and often perform very well. Now, these tools are generally trained on a very large number of software repositories. And in particular, GitHub Copilot is trained on all the public repositories on the GitHub platform. That is not a very small number, because just on GitHub we have more than 28 million public repositories. And starting from this vast number of code base, GitHub Copilot can understand which are the pattern in the various programming languages, how to use a specific API in a given context. Well, the problem is that in this large training set, there could be also your code. That could be just a few repositories or some sparse contribution in other projects. So GitHub Copilot has a very limited knowledge about you, because he knows only the code that you publish on GitHub, or as the same apply for the other large language models. And every time that this developer triggers GitHub Copilot, this suggestion is also limited to the knowledge base of these large language models. The same apply for an organization that probably can host more repository than a single developer. But what happens in a real scenario is that they don't share code, because probably it's related to customers, clients, and so it's private and must not be shared. So GitHub Copilot knows nothing about the routine methods or the configuration strings that are often used in this project. This will lead to suboptimal performance when we use GitHub Copilot for code completion tasks. And this is the reason why in this seminar, I'm going to show you an empirical study we performed to understand whether a second training of these large language models on a more specialized corpora, that is code written by a specific developer or organization, can improve the performance of these tools when used by the specific developer or an employee of an organization. And we started, first of all, by collecting data, of course. We selected an organization from which retrieve this data. That is the Apache organization that hosts thousands of projects on the internet. And the main goal, of course, of this mining is to retrieve developers and to profile these developers in such a way that we have a dataset containing all the code written by that specific developer. To do so, we mine the commits of this project. And in particular, we don't collect all the contribution of the developers because we want to simulate the code completion scenario. So in the case of modified line that will impact just a single token, this kind of contribution could not be significant for the completion scenario that, as I said before, is used for recommending the next few token lines or code block. This is the reason why we only collected the lines written from scratch, in particular single lines or entire code block that was written from scratch from that specific developer. And starting from these lines, then we can start to generate this dataset. And to do so, of course, we have to simulate the code completion scenario. So let's say that we mask a random number of tokens starting from this instance, from 3 to n-1, 3 to avoid trivial completion. And after selecting this random number of tokens, we mask them. So we are simulating the scenario in which the developer is triggering the tool for asking a suggestion. So each instance of this developer-specific dataset has an input and an output. An input that is the masked code, the one that requires a suggestion, and the mask that is the expected completion. That, of course, is the code written by that specific developer. Now, we collect contribution over the time, and we split this dataset in 3 parts: for the training set, for the evaluation set, and the test set. In particular, this splitting is performed over the time so that we are using contribution of the past to evaluate future changes. And also, we create this dataset for 100 developers that are selected by number of contribution in the Apache organization. That means that we have 100 developer, 100 training set, and 100 models that are developer specific. So in this case, we can create a very large scale empirical study. Now, for each developer, we also generate an organization-specific dataset. Why we do that? Because we want to understand whether it's more worth to have a single developer, a single model for a single developer, so a developer-specific model, or an organization-specific model. In the first case, it will be more difficult to maintain because we will have several models to maintain. In the second case, it will be easier since we will have just one model and can be used from all the employees of that organization. Now, we created this organization in such a way that it includes the contribution of the developer and also the other of the 100 developers of the organization. Of course, paying attention to not using contribution of the past for evaluating future changes. And for the training of the model, we used a transformer architecture, in particular the T5 architecture in 2 variants, the small and the large, to understand whether the result holds also for bigger models, and also to see if this result can scale up with bigger sizes. And we started also by pre-training this transformer model. We did not rely to already pre-trained models because we want to test the scenario in which the model have never seen the code before, in particular the Apache code. So in this case, to be sure, we pre-trained from scratch this transformer model without including all the Apache methods. And then we fine-tuned our baseline on top of 2000 GitHub repository that, again, are not related to Apache. In this case, we can consider this baseline as GitHub Copilot or the other large language models that are trained on a general knowledge and are used for returning our response. Now, for each developer, we then created a developer-specific model. We do that by with a second fine-tuning of this baseline on top of the developer-specific dataset. And we created also an organizator-specific model that is created again, further training our baseline with the organizator-specific dataset. For the evaluation, we used two metrics. The first one is the exact match. Basically, we check if the prediction of our model is exactly the same of the expected prediction. And the crystal blue, that is what they use to understand the code similarity between two snippets of code. Now, talking about the results, let's start by talking about the developer-specific models. We found out that out of 100 developer, the developer-specific model returned better result than our baseline in 78 for 78 developers. And in particular, we found out that we had an improvement, an average improvement of the model accuracy of about 5%, with 32 developer reporting a statistical significant accuracy. And it is not just a matter of numbers, because looking at the quality of the suggestions, we found out that the developer-specific model can really suggest personalized recommendation. So if we look to this method to complete, that was took from one test data set of a developer, of one of the one that the developer mentioned before, the baseline recommended this suggestion, which is of course wrong. It's wrong because he's performing some wrong assumption on the name of get column value method that does not exist in the project, as well as for the column variable. So he's performing wrong assumption on the structure of our code base. The developer specific model instead correctly inferred the red property method, that is what is used by the developer and in the project to retrieve data, and also the long varchar column configuration, so leading to the correct prediction. Talking about the organization-specific models instead, we found out that 92 developers benefited of this second fine-tuning with respect, if we compare the results with our baseline. And in particular, also the results are even better than the developer-specific models. As you can see, the average improvement and the statistical significant results are higher than before. So if we check the number between the organization-specific and the developer-specific improvement, those are the results, meaning that an organization-specific customization is often the best choice, and also the most practical in a real context, since we would create just a single model. Now, in this study, we also perform an analysis on the training data size, because we just say that the developer-specific models works worse than the organization-specific one, but the second was trained on more data than the first one. In particular, as you can see from this slide, in which we take the dataset with the maximum instances, the difference is very evident. So we performed another study to understand whether the improvement of our models are just because we added more training data or not. And to do so, we started with developer-specific models, and we compared that with an organization subset models. That means an organization-specific model trained on a subset of an organization-specific dataset. And then we did the same for the organization, because we say that the organization also works better than the baseline. And of course, the baseline was trained with less data. This is the reason why we compare the organization-specific models with a baseline plus model. That is the baseline further trained on more data, on the same amount of data of the organization-specific dataset. As a result, we found out that the developer-specific model works better than the organization subset, meaning that the customization that is personalized, specialized on that developer works better than having just more data. And the same applies for the organization-specific model, having the best result than the baseline plus. Now, as last point of this study, we also studied the impact of the model size, because as I said before, we used two variants of our model, the T5 small and T5 large architecture. And we found out that, of course, T5 large can have better result in terms of accuracy than T5 small. But the most important finding was that the same trend observed in T5 small prediction is also observed in T5 large. That is, our results does not depend on the size of the model that we are using, and that it can scale up with bigger model. So to sum up, customizing deep learning models for code completion tools makes sense. And also, the most important finding of this work is that the more specialized the data, the better are the results and the improvement that we can obtain from our models. Of course, in this study, we did not cover some important point like hyperparameter tuning. We use default settings because it will be more expensive since we train more than 2,000 models. Also, we just applied a simple fine-tuning of these models. So we could explore different way to improve the learning of the models, for instance, with reinforcement learning. And finally, a future direction that will be probably the most important one. Now we are still talking about fine-tuning and training a model that is expensive, also require a lot of resources, and in most cases is not really feasible. So a future direction will be to explore in context learning solution that does not require the training of the models, and so it will be just a matter of prompt engineering. This is everything for my seminar. Thank you for your attention, and if you have any questions.